Hi, I'm Kevin Deierling with Mellanox Technologies, and I'm going to talk a little bit about how we're transforming the data center. Mellanox has been committed to the OCP Open Compute project really since the beginning. We've made multiple contributions to OCP. Last year we actually contributed both our 100 gigabit Ethernet adapter OCP cards as well as our open optics MSA. So this is a WDM technology that there's a MSA, so a multi-supply agreement. We made that contribution. The other contributions that we've made involve our switches, both the previous generation, which is our switch X2, and then our 100 gigabit switches, which is our spectrum-based switches, which is 25, 50, and 100 gigabits. So we're very excited about what's happening. We have an end-to-end technology portfolio. So because we build silicon, we build the adapters, we build switches, cables, we can optimize everything end-to-end. So at this OCP conference, we actually introduced a whole bunch of new things. So as I mentioned, last year we introduced the 100 gigabit per second adapters. That was our ConnectX-4. This year we actually did 25 and 50 gig adapters as well, both single host and multi-host. So the multi-host is the technology that Facebook showed last year, and that was in the Yosemite platform, where they actually can take a single adapter and share it between 4 different CPU server blades. Today, we were announcing the newest generation of these products. This is the 25 and 50 gig. We really think that 25 is the new 10. And I'll talk about why here in a second. In order to have a device that really makes that claim true, you can't have it have 4 times the power and 4 times as expensive as for example, 10 gig. It needs to be very close in both price and performance and power, but 2.5x in terms of the bandwidth. So that's what we've done with these optimized devices, which are based on a specific silicon called ConnectX-4LX. The other thing that we're showing is our spectrum-based device. That is our next generation 25, 50, and 100 gig Ethernet switch. I'll talk some more about that in a second. We call it Open Composable Network. And you heard today in the sessions, they were talking about disaggregating the software and the hardware. So I'll talk about what Open Composable Networks is. The third thing that we announced here, and will be actually a session later, is a 100 gigabit Ethernet reference architecture with Netflix. And so we introduced this. If you're from the Bay Area and you're watching the most recent version of House of Cards, you were probably watching that on 100 gigabit Ethernet. So some people are thinking this is future technology. Who's ever going to need those kinds of speeds? We need it today. You've got millions of people watching videos. You need this technology today, and it's being deployed today. So in terms of the servers that we support, we really have the broadest platform of server support in the industry. You can go over our booth, which is right there. We're showing all of these platforms, which is the Yosemite, which was introduced last year, the Leopard, which was introduced earlier this year. These are OCP server platforms. We are also showing a Barrel-I, which is a rack-space platform based on the Open Power architecture. So this is the Power CPU from IBM in that architecture. We're doing that with our ConnectX-4 and our ConnectX-4LX. So this is the 100 gig, as well as the newer 25 gig and 50 gig parts. So we're showing this really across all sorts of different servers that we're demonstrating here. And I talked about the fact the need for 100 gigabits per second. This was actually from a demonstration that Microsoft did at their keynote event earlier last year, so in May of last year, at their conference. What they showed was that with 3 NVMe drives, they were able to saturate 100 gigabits per second link. And they did that with a special technology that we have, which is called RoCE. And RoCE stands for RDMA over Converged Ethernet. And what RDMA is, it's a way to move data very, very quickly between server nodes or between server and storage without involving the CPU. And so what was interesting is they actually ran the test with and without RoCE. So they ran the test using a software transport, and then they ran it using our hardware. And what they saw is that when they ran it without the Rocky, they got about half the throughput. They got about half the throughput. So instead of getting 100 gigabits, we actually got about 94, 95 gigabits, which was line rate for the packet sizes we were using. They got half of that. And what was really interesting is when they looked at why, and it turns out that the CPUs were completely maxed out. They were at 100% CPU utilization, trying to move the data. And so they couldn't move the data as fast as this 100 gigabits. So not only do we give you the full line rate, but we actually give the CPU back to you, because our adapters do, with Rocky, do all of the things that normally you would do in a software transport protocol stack. So the sequence number checking, the acknowledgement, we even do the user space the user space address translation. So we put the data directly into user space. Normally you go through the MMU to do that. When you're using hardware offload, you actually need the adapters to do that, and we do that as well. So to get 100 gigabits per second performance, you actually need this technology. So the other really big announcement that we made here at OCP is what we call open composable networks. And you heard it today from some of the telco vendors that were up there. They said they want composability. So what does composability mean? It means that we've taken the individual pieces of what normally is locked inside of a box. So if you buy a proprietary switch platform from a vendor that combines their software, their management stack, and all of the hardware together, that's what you get. You get whatever they're willing to give you. And if you want to add a new feature or a new capability, then you need to go knock on the door of that vendor and ask for that feature. And maybe it gets into the next product generation, maybe the next one, maybe the next one. The idea of open composable networks is really to give to enterprises and smaller organizations the same level of flexibility and composability as the big guys have. So the big hyperscale vendors today. And there's three pieces that you need to do that. The first is open platforms. And so we call this Open Ethernet. This is a platform that basically you can get with an operating system from us, or you can get it without an operating system. And ONI has really been one of the key things that's enabled that. ONI is the Open Network Install Environment. You can think of it as Pixie Boot for switches. But on top of that, you heard today about SI. So Microsoft was talking about the switch abstraction interface. And rather than being locked into a single vendor, the switch abstraction interface lets you write to an abstraction for the hardware, the underlying hardware, which is really important if you're going to have multiple network operating systems. So that's the second piece, open platforms. The second piece is these standard APIs. SI is one of them. It's a user space implementation, but there's also, in a kernel-based implementation, SwitchDev. And the third piece is network automation. And so we have a package that we call Neo. It does all of the network orchestration and management, but we also use Neo as the integration point with all kinds of other management packages. So that's where we interface to SDN and other packages. So together, these three things are what we call open composable networks. We wrote a blog on it today. It's really like Lego. You think of it as standard APIs. Why is Lego so cool? Because you can build anything you need with it. So if you want a new function or new capability, all of these are standard APIs. They let you migrate very quickly to the absolutely best hardware that's available. And so that's what we think is by having these open platforms that we will actually compete no longer by locking people in to a proprietary platform, but rather on whoever has the best hardware. And we believe that we have the best hardware here. One of the key things that we're demonstrating is really the vibrancy of that, which is all of the different network operating system vendors. So earlier this week, we announced support from Cumulus. So now Cumulus is running on our Spectrum switch. Microsoft Sonic, which was just introduced today, we're demonstrating that. OpenSwitch, which is the HP open source initiative for a network operating system, is running that. We have our own network operating system running on top of that, as well as Metaswitch. So really this is the idea of open composable networks, is to take best-in-class software, whatever you need, best-in-class hardware, standard APIs, and management and network orchestration, so all of the automation. So I made the claim that we have the best hardware platform in the business. And I want to back that up. So today we are demonstrating our Spectrum platform. A couple of the things that you should be thinking about is the packet forwarding rate, microburst resilience, and fairness. And today we have the highest packet forwarding rate in the industry, 10 to 15 times better microburst performance, and I'll talk a little bit about what this means. We have the best fairness, and it's very predictable. So we really talk about predictable performance here. One of the things, if you're debugging an application, you're writing things at an application level, you don't want to try to figure out something that's happening beneath you that's buried in the network. And so we think this predictable performance is very important, and we offer the best in the industry. And today we published a Tolly report that compares our device, the Spectrum, with the Broadcom Tomahawk silicon. And you should read that, go online. We have it at our booth. You can come ask for it. One of the keys here is it's 0 packet loss. And so we don't drop packets. We don't drop packets unless there's a situation that it's unavoidable to drop packets. And then we're 10 to 15 times better than the Broadcom silicon. But in many cases, the Tomahawk silicon is actually dropping packets. And any platform that's based on that, it's in the ASIC, so you can't get away from that. So what's causing that? One of the things is buffer management. So there's a situation called incast, where you have 2 ports going out to 1 destination port. If I have 2 25 gig ports trying to go out 1 25 gig port, there's nothing you can do. Sooner or later, your buffers are going to fill up. So it has to do with the efficiency, how long you can tolerate a microburst associated with that. And it turns out we actually have very efficient buffering. We have an entire integrated buffer, whereas the competition here actually has split their buffering up, and we see about 10 to 15 times better packet loss. So in terms of the microburst size that were characterized in the Tolly report, we don't drop packets, and the Broadcom device does. And this is showing the difference between the microburst size that will actually cause a packet loss to occur under the situation of incast. And so this is the comparison between the Spectrum and our competition's device. You can see we're anywhere from 9 to 15 times better in terms of the performance. So this is published, it's online. You can go look at these graphs, and there's lots more detail associated with that. But an even bigger thing is avoidable packet loss. There's many situations where you don't need to drop packets. This is just a packet forwarding limit. So if you're having, port number 1 talk to port number 2, and 2 talk to 3, and 3 talk to 4, your ASIC should be able to handle that. If you say that you have a full wire speed line rate ASIC, it should be able to handle that. And in fact, you can see in this comparison, across the board, we don't drop packets. So we can handle full line rate from 64 bytes all the way up to mega packets at 9K jumbo frames. And if you look at the numbers here, 32 ports at 100 gigabits per second requires 4.76 billion packets per second. Anything less than that means that it's not a line rate, full wire speed across all packet sizes. So this is avoidable data loss, and simply it shouldn't happen. You shouldn't have to worry whether your network is dropping packets, not because of congestion, not because of an incast situation, but because of the underlying hardware in the switch, and we don't do it. The last piece here is fairness. And so again, if you have a bunch of ports connected up, okay, if you have 15 or 16 ports, or 4 ports, you would expect completely balanced data between the different packets here. And you shouldn't actually care where your virtual machine is running. So whether it's running on a one node or a different port, or if that virtual machine migrates from one port to another, you should see completely balanced performance across the board. And so really we see predictable performance and fairness across the board. So with that, I'll wrap up. I'll invite you to come over, see the demos. We're actually showing a bunch of different network operating systems running on top of the Spectrum. We're showing our Neo platform, a bunch of different vendors, our partner Cumulus. We're showing Microsoft, OpenSwitch, Metaswitch, and of course our own network operating systems. So thank you very much.